So the things that we're doing now, we're doing 3 lesson days, and then we're gonna have a quiz, probably like a double weighted quiz, because it's kind of on miscellaneous topics. It really doesn't fit well into a chapter kind of thing. This next thing is we're supposed to learn, and I think you can see the objectives here. These come from our SOLs. Our SOLs were supposed to do nonlinear systems of equations. You already did linear systems equations in Algebra 1. Probably don't remember it very much. So today's lesson is we go back and we review that. It is actually in our book. It's just not actually in our SOL. And then we do one more class where we actually do the nonlinear systems. So systems of equations. You guys need to stop talking. Yeah. You know, it's just a constant disruption. That's what it is. Okay, systems of equations. A system of equation means more than one equation, right? Generally, if you have as many variables as you have equations. So if you have a system would be 2 equations with 2 variables or 3 equations with 3 variables. You know, it could be any. It could be, I could say that when I was programming computers or learning about how we model the atmosphere, that was 7 equations and 7 variables. They weren't linear systems, but they were 7 equations, 7 variables. Now, what we're going to do, what we do in this class is only the 2 by 2, right? 2 equations, 2 variables. Okay. Hurry up. Okay, linear systems of equations mean both lines are linear, right? How do you know when an equation represents linear? It means both the x and the y are to the first power. The exponents are 1, which generally means you don't see an exponent. Right? The whole system is considered to be nonlinear if one of those equations is nonlinear. If one of them has an exponent on x or y, which is not 1, then you got a nonlinear system. And the SOL specifically address 2 situations. Linear quadratic, which means one is a straight line, one is not. And quadratic quadratic, which means neither one is a straight line. Now, what is the shape of a quadratic? If I graph a quadratic function for us up till now, what was that? Anybody? Ever hear of a parabola? No, forgot all that too, huh? Well, that's actually not the correct answer here either. Quadratic is one shape, or sorry, a parabola is one shape for a quadratic, but there's actually 4. And when we get to the nonlinear systems, it's actually coming out of chapter 10, where they deal with all 4 shapes. And I will show you on the next slide what those are. Okay, The solution to a system, are the points that satisfy every equation. If it's just two equations, then it's the points that would satisfy both of them. If you graphed them, it would be the intersection point. Wherever they cross, that's the answer. In my experience with these SOLs is that usually there'll be maybe two questions that are about systems. And one of them will be a graph where you can see both graphs and you just see where they cross. That's your answer. So that's understanding the point that the solution to a system are the intersection points of the graph, right? There's three possibilities when you're dealing with straight lines. One possibility is they cross. They have different slopes, so they cross at one point. Right? Another possibility would be they have the same slope and different y-intercepts, so they're parallel, which means the system doesn't have any solution because there's no shared points. No points on one line or on the other line, so no solution. And then if both equations actually represent the same line, that means one line is on top of the other. That means they have an infinite number of shared points. Those are the three possibilities, at least for straight lines. One solution, infinitely many solutions, no solutions. And we'll see what all three of those look like. Now, the linear quadratic possibilities. Actually, so here's the parabola that we're familiar with. But there's actually more possibilities than just that. A quadratic, although it wouldn't be a function, could be all what we call the conic sections. Ellipse, right? Circle, and this is called a hyperbola. It's actually the shape of the graph with an inverse variation. Remember how we would sketch one part in quadrant 1 and one in quadrant 3? That's called a hyperbola. Let's see if I got that right. Let me make it like that. Okay. Now, try to imagine how many solutions, how many different ways could one straight line cross with, let's say, this ellipse right here. What's the most number of points that a straight line would intersect with that? How many intersection points are there? 1, 2. 1, 2. 2 solutions. That's the most you can get from a straight line and a quadratic. Now you can move that around. It doesn't have to be 2 solutions. Let's see if I can get that. Come on. I want to move it around like that. Doesn't want to let me grab there. Oh no, not the whole thing. That's why it's not letting me do it. Let me do this again. Yes. Let's go like this. See if I can grab that. Edit. And then do that again. Where I make my line go off the page like that. So you could have a cross in 2 points. You could have it cross in maybe 1 point. Or it could not cross at all. So there's all three are possibilities here. Okay. What if it was a parabola that we're looking at? It's still not letting me do that. What about down here? How many points can a straight line cross a parabola? The most, 2, or it could be 1, or it could be 0. What about if we go to the other side? 2 points? Could it be 1 point? Yeah, it could be. If it was in between, like something like this. Watch if it goes like this. And it just barely touches one of those branches like that, that would be 1 point. Or it could be none. And a circle the same way. 2, 1, 0. So one of the SOLs says we should be able to predict the number of solutions to a linear, quadratic, quadratic, quadratic. Okay. Now, if it's a quadratic, quadratic, now you got to try to imagine putting those shapes together. I mean, what if I had a parabola and an ellipse? A parabola looks like this, and an ellipse looks like this. Can you imagine the most number of points of intersection you could get between those two? An ellipse is longer in one direction. What would be the most points you could intersect with those two if you laid one on top of the other? What if your ellipse was like this? Now you got 4. So you can, if you have a quadratic system, you can get up to 4 intersection points. You know, and you could do the same kind of drill with any of the 4 shapes. I mean, even if we had that hyperbola, right, and an ellipse, 4. Right. Circle and a parabola, 4. That doesn't mean you have to have 4. You could even have 3. What if I had an ellipse like this and a parabola that came down and touched one side and went back the other way? 1, 2, 3. But like I said, today we're just going to do the linear. And we're going to use, these are the 3 methods. These 2, substitution and elimination, they should be reviewed. If they're not, it's okay. That's why we reteach it. The graphing is probably new, and I think there's 2 homework problems. You need to do them in class because you have the calculator. So when we get to the end, do those first. If you're sitting here with the calculator and you've got time, there won't be an excuse next class to say, I didn't have a calculator, right? Do those when you're here. So substitution, these are the steps, right? You have 2 equations and 2 variables. First, you solve one equation for one variable, and you choose. You're going to look at the equations and decide which one makes the most sense to solve for the variable. Then you're going to substitute for that variable in the other equation. Once you do that, then you've got one equation and one variable. That turns it into a basic algebra problem that you can solve for the one variable. So remember, the solution is not just the value of one variable, it's a point. After you've solved for the first, you're going to substitute that answer back and try to find the second variable. I think I got them up. No, I don't. So finish that, Nathan. Okay. So first step, here's the 2 equations and 2 variables. What does it say the first step? Solve one of these equations for one of the variables. Okay. Which variable would you think would be the easiest to solve for in these 2 equations? Does anybody see it? The first one for which variable? What's that? Now, there's another obvious choice here. Chris, the second equation for y. Because there's a 1 in front of the y here, that'll be easier to solve. If in these here, if I solve this one for x, I have to divide by 3 in the last step, and that could make me create some fractions, and I don't want to deal with fractions. Same thing if I solve for the y here or the x here. In the last step, I'm probably making fractions, so you don't want to do that. So probably you're going to want to go look in the two equations. If there's one of them that has a variable with a coefficient of 1, that's the one you want to solve for. So this is the obvious choice. If you go for one of the others, you can still be right, but you're going to make it a little harder on yourself. Right? So this one, when I solve, will be y equals negative 2x plus 10. That was step 1. Just subtract 2x from both sides. Right, what did the second step say? Okay, since we solved for y here, right, we're going to substitute for y here. Right, so in the place of the y, we're going to put negative 2x plus 10. 3x plus 4 times negative 2x plus 10 equals 12. That's the step 2. Right? By doing that, now we have one equation and one variable, and that should be fairly easy to solve. Right? That's distributive property 3x plus negative 8x plus 40 equals 12. Combine like terms, 3x plus negative 8x. Subtract 40. I don't like this problem. Divide by 5. Okay. So what does it say to do there? Now that we've solved for that one variable, what do we do? What's it say? Just wrote down the steps. Right. So go back and substitute that answer into this equation. Right. This thing that you made at step 1 is the perfect place to solve for the other variable. So now we're going to go here. This is the step 4. Y equals negative 2 times 28 over 5 plus 10. Y equals negative 56 over 5 plus 50 over 5. Why did I write 50 over 5? Why did I write 50 over 5? Yeah, because we got to add fractions here, right? This thing has got a denominator of 5, so I'm going to make 10 into a fraction, 50 over 5. So y equals negative 6 fifths. So the point where these two graphs would cross would be 28 fifths, negative 6 fifths. So try to do the same thing with those. Here's the steps. They're written right there. That's your first U try. Which equation did you solve for which variable? The first one for which variable? Yeah, probably you should be starting by solving the first one for x. Anybody get an answer? Yes? Okay. Anybody get an answer? Gail? Did you get this far? Solve for x, substitute for that variable in the other equation, so it looks like that. Now you can solve for the y. That's the only thing that's left. Let's throw that away.
Oh, yes.
Okay. How many got 5 halves for y? Got that far? Then what do you do with that? Right. Once you get to y equals 5 halves, hopefully you got that. Then you're going to plug that in here. Right. Right. So I put it in place of y, put the 5 halves. 5 minus 3 times 5 halves. Then 5 equals 10 halves. 3 times 5 halves is 15 halves. 10 halves minus 15 halves is negative 5. Now, elimination is another method supposedly you've been taught. And I've left the first step as blank because when you first do elimination, you don't have to deal with the first step. So just to keep it clean, we'll just use steps 2 through 5 for the first couple. Now, usually, not always, but usually if you do elimination, you're going to have the equations in standard form before you start. And for a line, standard form means ax plus by equals c, meaning you should have the x and the y terms on the left and a constant on the right. And generally, the two equations are written like the last two that we saw, with the x's lined up and the y's lined up and the constants lined up. Everything's all lined up. So here's a system of equations. Both lines are in standard form, the ax plus by equals c. And the variables, the x terms are lined up, and the y terms are lined up, and the constants are lined up. The equal sign is lined up. Okay. What does it say to do once is the second step? So just add these up, right? Make a bar and add up the x terms and the y terms and the constant terms. 4x plus negative 4x, they cancel each other out. They eliminate the x term. That's why it's called elimination, right? Cancel. 2y plus 3y, 5y. 9 plus 16, 25. Solve for y. So I think, what was that? Step 2 was to add them up, and step 3 was to solve. And now what do you do with that? Right. So you want to go back up to one of these two that you started with. It doesn't matter which one. You can choose. If one of them looks easier to solve, then go for it. Right. But either one will give you the right answer. Anybody have any choices here? Which one you want to solve? Why? Because it's what? Yeah, I mean, I would look at that negative 4x and say, I think I'd rather skip the negative. So let's go over this way and go 4x plus 2 times 5 equals 9. 4x plus 10 equals 9. 4x equals negative 1, x equals negative 1/4. So there's our point, right? We know they're intersecting in a line. That line is, the point is negative 1/4, comma 5. So try to do the same thing with that one. Who got an answer? Deshaun, you can answer? What'd you say? Y equals 0 and x equals 4. How many got that? 4, 0. Right? So when you added these two up, again, you eliminated the y's in one step. Negative 2x plus 5x is 3x equals 12. X equals 4. Right, so which equation did you substitute for that? The second one? It doesn't matter. I would have probably done the first, but it does not matter. Let's do this one, because Jataya said to do this one. 5 times 4 minus 8y equals 20. 20 minus 8y equals 20. Subtract 20 from both sides. Negative 8y equals 0. So what does y equal? 0. So y equals 0. So the point is 4, 0. Okay, now we got to fill in the missing step. Right? In the missing step, which is not always necessary, because like the two that we just did, you could add them up and eliminate a variable right away. Most of the time, that's not true. Most of the time, it's like this system here, that the 2x and 3x, if I added those up, they would not eliminate a variable. Neither would the y's be eliminated. So you got to choose some numbers to multiply by each equation so that you create the opposite coefficients that you want. And you can see that this has already been done for us right there. What does it look like they multiplied times the first equation to make that equation? What constant did they multiply by this to make this? 3, right? If you multiply everything times 3, you get that. So usually you have to choose that, right? Find some value, and you don't have to everybody pick the same thing and still get the answer right. So let's say 3 times 2x is 6x, 3 times 7y, 21y, 3 times 4 is 12. What does it look like they multiplied the bottom equation by to make this? Negative 2, right? So negative 2 times 3x, negative 6x. Negative 2 times 5y, negative 2 times negative 5 is positive 10. Right? When you do that, when you multiply by a number, it changes it, but it actually would still have the same solution. The system still has the same solution. It's called equivalent system. So that missing step 1 is multiply one or both equations by a constant or 2 to create those opposite coefficients. Now, once you've got an equivalent system with opposite coefficients, you're going to solve it like we solved the first couple. Just add them up, eliminate a variable. Right? Add them up. The x's cancel. 21y minus 10y. 11y equals 22. Y equals 2. And then when it says to go back, substitute your answer into one of the original equations. You could substitute into one of these, which is really not one of the original equations, or you could go back to these, which are going to be smaller numbers involved. Either one, pick an equation you want to solve. I think that's why it says you choose. You choose where you want to go, and now you got 4 options. How about we pick? What did we just solve for? We solved for y. So I'm going to put it in this one. 2x plus 7y equals 4. 2x plus 7y equals 4. Y equals 2. 2x plus 7 times 2 equals 4. 2x plus 14 equals 4. So 2x equals negative 10. That was sloppy. Negative 10, x equals negative 5. So the point is negative 5, 2. So go ahead, try to do the same thing there. Yeah, try it on elimination using these steps. Remember, it's up to you which variables you try to line up, Would you rather make these cancel, or would you rather make these? You just have to pick. It's kind of like finding a least common denominator, right? What's the smallest number that both 3 and 5 divide into? 15. So maybe you'd multiply this one by 5 and this one by -3. Or 7y, 2y, maybe you'd do this one by 2 and this one by -7. You get to pick which way you want to go with that. It's March 2nd. Well, you may be doing it different than this, right? You may have tried to make the y's cancel. I made the x's cancel. Okay, quiet, please. So you can see I made the x's cancel by multiplying times 5 and -3. You might have chosen to cancel these. You might have done -5 and +3, right? It doesn't matter in the end. You should get the same answer. I got the y is 3, and then I plugged into the first equation for y and solved for x. Now, a couple of special cases are these here, where you can see in this one that when you add to cancel to eliminate a variable, it actually eliminates both variables. Right? If I add those two together, negative 3x plus 3x cancel, y plus negative y cancel, and actually on the right-hand side, the negative 5 plus 5 is 0. So you end up with an equation which doesn't have a variable in it anymore. So it actually does not depend on the variables. Now, is that statement true? Does 0 equal 0? Yeah. If it does, that means it's the same line scenario. One line is on top of the other because that's a true statement. There's infinitely many solutions. There's not just one. It does not depend on the x and the y. So this is true. So this is always true. Always true. Same line. Right. If you add the equations like this one, and it cancels the x's and it cancels the y's, but now on the right-hand side, I've got a number, not 0. So it says 0 equals 16. Is that true? It's not true. So this is the parallel line scenario, right? It does not depend on x and y because there's no x and y here. But because that's a false statement, there's no solution. They're parallel lines. False. No solution. Parallel lines. Okay. So here's your last few try. One of these is a no solution. One of them is infinitely many solutions. Which one is the no solution? I mean, these are not already opposite coefficients, so you're going to have to do something to make that happen. Which one is the no solution? I mean, what would you multiply in this first one so that you had opposite coefficients? Which one would you multiply? The first line you would multiply by a 2, right? And now that is negative 2x plus 2y equals negative 2. The bottom is unchanged. So is that going to be no solution or infinite solutions? Right? The x's cancel, the y's cancel, and what do you have on the right-hand side? Negative 2. So what does that tell you if 0 equals negative 2 is the result? Is that a true statement or a false statement? False. No solution. What about this one? What would you multiply so that you can eliminate a variable? What am I going to multiply this line by? How about negative 3? And when I do that, right, that's going to give me negative 18 plus 18, which is 0. So when I add these up, 0 equals 0. What does that tell you? Which means the two lines are the same line. That means there's infinitely many points that are on both lines. The way usually you would say it is you would say no unique solution. There's a solution, but there's not just one. It's not like when the lines cross at one point. That would be a unique solution. in a minute. So I'm going to come around to initial. Okay. So we're going to have to save what else I had planned for next class. There's the homework, but don't do these because we're just going to be able to solve the systems, but not do the solve the graphing because we didn't do that yet.